In Chapter 4, we're going to be evaluating triangles, looking specifically at understanding different properties of triangles, and then showing how different triangles can be congruent with each other. Beginning in Lesson 4.1, we start with is classifying triangles by either their sides or by their angles. As we can see here, we have scaling triangles, which says all three sides are different lengths, isosceles triangles, where two of the sides have the same length, and an equilateral triangle, where all three sides have the same length. When we classify by angles, we have acute triangles, meaning that all three of the angles are less than 90 degrees, a right triangle, which means one of the angles is a right angle, an obtuse triangle, which means one of the angles is greater than 90 degrees. And last is an equiangular triangle, which means all three of the angles are the same measurement. When we look at a coordinate plane, the way we can determine the type of triangle it is by applying the distance formula to each of the sides. Since we have the coordinates of all three of the vertices of the triangle, we can find the length of this leg, the length of this leg, and the length of the third leg, all three using the distance formula. When we do that, we find that each side of the triangle actually has a different length. And because of that, the way we would define that based upon its sides is a scaling triangle. Remember, a scaling triangle is one that all three sides are different lengths. In this example, we would do the same thing. We would look at the distance between A to B, B to C, and then A to C, evaluate all three of the sides, and then determine what type of triangle it is from a side standpoint. Again, it can be either a scaling triangle, an isosceles triangle, or a equilateral triangle, all three sides together. As we look at triangles, we also begin to look at the angles. Angles that are inside of the triangle itself, those are going to be interior angles. And angles outside of the triangle, these would be interior. Outside the triangle are called exterior angles. And an exterior angle is created by taking one of the sides of the triangle and extending the side, and then looking at the outside angle from one of the other sides that it connects to. So in this case, each of the exterior angles plus its associated interior angles, we're going to be looking here at a linear pair, and we know those are going to add up to be 180 degrees. I think everybody knows that when you add up the measure of the angles, all three of the interior angles of a triangle, it adds up to 180 degrees, which is independent of the type of triangle it is. It always has to add up to 180 degrees for it to actually be a triangle. When we begin then looking at the exterior angles, what we're going to find is that an exterior angle is going to be equal to the sum of the opposite or the non-adjacent interior angles of the triangle. So angle 1 here is going to be equal to the measure of angle A plus angle B. Now we can go through and prove that if we wanted to by using the relationship of these being supplementary angles, essentially all three of the triangles adding up to 180, and so that we know that this has to equal that, because both of them plus angle C would then end up being 180 degrees. The key thing to remember is that the exterior angle is going to be equal to the sum of the non-adjacent or the opposite side angles from the triangle itself. The way we can use that to solve and find the measurements of all of the angles is that in this case we know the exterior angle is 2x minus 5, and then one interior angle is x, the other is 70. These are the opposite or non-adjacent ones. And so we set these to be equal to each other. That's what this equation does. 2x minus 5, the exterior angle, equals 70 plus x, which is the sum of the other two interior angles. We go and apply our algebraic principles, and we can solve for x equals 75 degrees. The way we can check that is we can plug 75 into x, and we can test, do these then add up to equal each other? So there's almost always a way that we can test to see whether our math in solving for x is done correctly. When we're looking at a right triangle, what we know is that one of the angles is 90 degrees. Since we know the sum of all three angles of a triangle has to equal 180 degrees, well, if we take 90 degrees out, we've got 90 degrees left over. So these other two angles are going to be complementary. They're going to add up to be 90 degrees. We know that because all three together have to add up to actually be 180 degrees. Pretty straightforward corollary there. If we want to look to see how we would apply some of these principles, in example 3, we have an exterior angle, which has x in the equation, and our two non-adjacent interior angles also has x in it. One of them does. So we can set this up similar to the other example, and we can say 5x minus 10 is going to be equal to 3x plus 40. And we can go through, and we get 2x is going to equal 50, and we're going to get x equals 25. The way we can test that then is 3 times 25 is 75. 75 plus 40 is 115. 5 times 25 is 125 minus 10 equals 115. So that checks out. Now, the other thing I can do is find the measure of angle 1, because I know 75 plus 40 is 115. So this remaining angle has to get me to 180 degrees. So that would be 65 degrees for angle 1. That's how I apply my different theorems. In this case, the relationship between the external angle and the non-adjacent internal angles, to be able to solve and then find all the measurement of the various angles within the triangle itself. Here in lesson 4.2, we're going to be looking at congruence and then ultimately, specifically, congruence of triangles. When we're talking about congruent figures or congruent shapes, that means if I were to take a shape and lay it on top of another one, they would exactly match up correctly. And so for these three, they are the same shape and the same size. If I stacked one on top of the other, it would look like just one shape. For this example, I can see that all three of the triangles are different. And because they're all different, there's not going to be congruence with any of these triangles. None of the corresponding parts across the triangles are going to match up, which has to be true for triangles to be congruent. So as we look at that, what it means is that if I have two triangles, triangle ABC and FED, what I notice is angle A and angle F match up, B and E match up, C and D match up. So all three of the angles have the same measurement, and that's represented by the little red arcs there. In addition to that, I can see this side, AB, matches up to FE, AC to FD, BC to ED. And so I know all three sides match up as well. Now that I've seen that all the angles and all the sides match up to be the same measurement, I know that these are going to be congruent triangles. So the way I call these or label these would be corresponding angles and corresponding sides. All of them are equal, so that my two triangles then are going to be congruent. When we're talking about congruence, we're actually talking about the physical piece of, in this case, the triangle. We're not talking about measurements. And that's why we use the congruent to symbol. And you can see that here being used to show which sides match up and which angles match up. So these are how we would write congruent statements of these two triangles, which are going to be congruent triangles. And we simply have to make sure that we are aligning the parts with the correct sides together. Same thing with the angles. When we align the sides correctly, then the angles should match up. When we align the angles correctly, the sides should also match up. So essentially what I'm going to be taking is one of the figures and rotating it in a way where it would lay exactly over the top of the other figure, and everything will match up so that the angle measurements and side measurements are equal. In this example, I'm specifically told that these two polygons, quadrilaterals, are going to be congruent. That's what my congruent symbol says. So now that I know that's going to be the case, what I have to do is figure out how do I rotate and match up the sides and the angles so I know which ones correspond to which. Well, one of the things that I can do is I can look at how the figures are drawn. Here I see it's D to E to F to G, and in the second one it's S to P to Q to R. That information tells me something. So it says that FG, this side, is going to be congruent to QR. It tells me how I would rotate the figures so that I start at the correct same vertice and everything lines up correctly. So now I can figure out my sides that relate to each other because I know FG is going to equal to QR. I know 12 is going to equal to 2x minus 4, allowing me to solve for x. For my angles now, when I do that rotation, I know that angle F here is going to correlate or correspond to angle Q, which is 6y plus x. So I've solved x here. I'm able to plug it in there. I can establish my relationship. And now what I've done is solved for both x and y using the information in the drawings based upon knowing that the figures are going to be congruent. I've got a couple of examples here. Again, I'm told that these two figures are going to be congruent. So it goes A, B, G, H, and then it's going to go C, D, E, F. What I'm going to want to do is rotate it, and then I will find that this angle and this angle are going to be the same. It allows me to solve for x. For this example, I can see that those sides are going to be equal. Those sides are going to be equal. And then these last sides are going to be equal. Because I know that all three sides are equal, then I know that those triangles are going to be congruent. What I would have to do is I would have to take and rotate this triangle like that in order to get this side to line up over here and this side to line up over here. You have to kind of visually manipulate these images to know exactly which sides line up, but most importantly, you're able to use the sequence of the vertices to help you understand which sides are congruent to each other. Going back to triangles, if I have two angles within a triangle that are equal to each other, then I know the third angle is also going to be equal. The reason I know that is because all three have to add up to 180, and if those two are going to add up to the same number, then the third one is what gets me to 180. So if I know any two angles of a triangle, then I know the third angle is going to be equal when I'm comparing two triangles like that. For this example, one of the things I have to do is I always have to be aware of how the drawing is representing the information I need. So this is one of the triangles I'm looking at. I have a second triangle, which, if I can move that, now I have a second triangle, which is going to be over there. I'm kind of separating them, if you will, so that I know which sides and which angles match up to each other. I know that that angle and that angle are going to match up. The little red arcs tell me. So the measure of angle B is also going to be 45 degrees. And I know the angle of this triangle and the angle of that triangle match up as well. They're both going to be 30 degrees. And so I've got 75 degrees here. The other angle that I'm looking for in both triangles, which will be equal using our theorem that we just looked at, in both triangles will be 105 degrees. A couple of other properties that we want to look at. So any triangle is again congruent to itself. That's called the reflexive property. The symmetric property says if one triangle is congruent to another, then I can draw it or write it the exact opposite way, because I know if this is congruent to that, then that is congruent to that. And then the third one is that if I know two triangles are congruent, so ABC is congruent to DEF, DEF is congruent to JKL, then I know ABC and JKL are also going to be congruent. Again, it's kind of the old, if A equals B and B equals C, then I know A equals C. It's exactly that type of concept. Now I'm just applying it to the triangles. Okay, in 4.3, what we're going to be doing is applying some of the things that we learned earlier to prove that two triangles are congruent. If I'm told that two triangles are congruent, then I know that their corresponding angles and their corresponding sides are going to be equal. Likewise, if I can prove that all three of the sides of both triangles, if their corresponding sides are equal, then I know the triangles themselves are congruent. That congruence is called side, 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 or SSS. Side, side, side congruence says that when I match up all three of the sides of the triangles, they're equal. So then by definition, I know the triangles are congruent. And remember, the length of the sides are equal. The triangles themselves are congruent. And so, if I look at this specific drawing, the question is, do I know, using side, 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 whether or not the two triangles, and I have one triangle which is here, and the other triangle which is there, do I know that those two triangles are going to be congruent? Well, the first thing I'm told is that those two sides match up. And the second thing I'm told is those two sides match up. Well, I'm only given two sides. What about the third one? Well, in this case in the drawing, the third side is actually the same for both triangles. So by definition, since it's the same, it is equal. So now I know that those two triangles are going to be congruent. And I've proved that by side, side, side reasoning. If we look at a couple of examples here, so in example number 1, we're trying to decide, are the triangles congruent? Well, as I compare this, those sides are congruent, those sides are congruent, the third side is congruent, So the answer in that one will be yes. If I look at this one, and I've got two triangles here, the problem is, while we've got two 7s that match up, and the 9 is the same, one is 4 and one is 3. Since those two sides don't have the same measure, those two triangles are not going to be congruent. And in the last case, I've got those two sides, and the third side. All three of the sides are equal in measurement. So yes, those two triangles would be congruent. In lesson 4.3, we were proving triangles to be congruent by using the concept of side-side-side congruence. Now we're going to continue to look at other ways that we can prove that two triangles are congruent as well. The next one is called side angle side. And it's very important because there's a very specific order here that I have to pay attention to. When we're talking about side angle side, the angle has to be the one that is included in both of the sides. It has to be the one, the angle that touches, if you will, both of the sides that I know are the same length, which is why it's called side angle side. In this case, I know those two sides match up, these two sides match up, and the included angle, or the angle between the sides, match up. So now I can say that those two triangles are going to be congruent because of side angle side congruence. It's really important to remember that the angle has to be the one that touches both of the sides that I'm talking about. So here's an example, going back to something we've learned earlier. I have two parallel lines and a transversal. So I know that this angle and that angle, those are going to be equal because they are alternate interior angles. Since the angles are equal and the two sides are equal, side angle side, side angle side, I can prove that this triangle and this triangle are going to be congruent by using side angle side congruence. The key thing to remember here is applying the fact that I have two parallel lines. The little red arrows prove that. I've got a transversal and I've got alternate interior angles. Using all of the information available to me, then I know that those two triangles are going to be congruent. Here's another situation where I have a diagram and I know, because they are diameters, that these two will match up because they're both going to be a radius. Those two are going to match up because they're both going to be a radius. So I have the two sides that I need. I also have the angle that I need because here I have, if I draw this out a little bit more, I have vertical angles or opposite angles, and I know those are going to be equal. So I have a radius angle radius, a radius angle radius. The angles are equal. Obviously, the radii are all equal. So I know that the two triangles that are drawn now in this circle are also going to be congruent. If I have a special triangle, which is a right triangle, and I know that because I have the right angle here, the way that I prove congruence is called hypotenuse leg congruence. So the first thing I have to do is remember that the hypotenuse is the side of the triangle across from the 90-degree angle. In my example here, I see that my two hypotenuses are equal, and I also have a leg that's equal. So I know those two will be congruent, these two triangles, because of hypotenuse leg. Again, the key thing to remember is that the hypotenuse is opposite the 90-degree angle, and then I need a leg for each of the two triangles that's going to be equal to each other as well. That way I can prove that the triangles are going to be congruent. So again, sometimes what I have to do is I have to take a drawing and redraw it in a way that's easier to see. I'm given a lot of information here. I'm told that WY and XZ are going to be congruent, and I'm also given the fact that these two are right triangles. When I break them out, like I do here, well, I was told that the hypotenuse of both are equal. I know I've got the right angle, so I'm working with a right triangle. And in this case, ZY and YZ, they're the same side. So I've got two right triangles with a leg that's equal. The hypotenuse is equal. So I know by definition, those two triangles are going to be congruent as well. Here's another example. I know I've got a right triangle here with a hypotenuse and one there with a hypotenuse. This tells me the hypotenuse is equal. Again, I have the same leg or the same segment that creates a leg of both triangles. So now I'm going to know that this triangle and this triangle are going to be congruent to each other because of hypotenuse leg. Key information here: equal hypotenuse, right angles, shared side. All of that means I've got HL congruence. As we continue on into lesson 4.5, what we're going to do is add a couple of additional ways to prove that triangles are congruent. So we started with knowing that side, side, side triangles are congruent. Side, angle, side triangles are congruent. The angle is the included angle between the two sides. And hypotenuse leg triangles, two right triangles that have the hypotenuse the same length and a leg the same length. We know those are three different ways to prove that triangles are congruent. We're now going to add a couple of more. One is called angle side angle, or ASA, and the other one is angle angle side. Exactly the way they're explained. Angle side angle says I have an angle and a side and another angle, and the side has to be between the two angles I'm talking about, and that matches up to an angle and a side and an angle of another triangle. Key thing here is that the side is the one between, if you will, or included with the two angles that are given. The angle side theorem says I've got an angle going to an angle going to then a side. Angle, angle, side. The side is not included. It's not between the two angles, but it literally is. I have an angle, then another angle, and then I continue on around and have a side. It's like I'm going in this direction. Same thing here, angle, angle, side. And when all of that matches up, just like I was looking at before, I can prove, or I know, that my triangles are going to be congruent. So if we look at this example, we're not going to go through the proof example the way they're talking about, but let's see what we have. Well, I've got an angle and a side, and a corresponding angle and a side. So I know that those two triangles are going to be congruent because of angle, angle, side. Again, pretty straightforward. I just match up my two angles, that with that, that with that, followed by my side, and I am able to know then angle, angle, side congruence shows me that those two triangles are going to be congruent as well. Here's a great summary of the different techniques that we've looked at so far in Chapter 4. Side, 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 angle, side, hypotenuse, leg when we're working with a right triangle, angle, side, angle, 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 side. These are going to be key ways for this chapter that you're going to be able to prove that triangles are congruent. And you're going to have to determine, based upon the information that is given, which of the postulates and theorems will apply to the triangles being compared. So it's really important to become familiar with recognizing how to decide what information aligns with which of these different postulates and theorems in order to then prove or say that, yes, the triangles are congruent. Likewise, if we know that the triangles are congruent, then this information helps me potentially solve for the length of a side or the measurement of an angle. In lesson 4.6, we're going to continue now and apply all of the techniques we've learned regarding triangle congruence to, again, either prove that triangles are indeed congruent or to help us then solve for potentially the measurement of a side or the measurement of an angle by knowing the triangles are congruent and then finding which of them correspond to each other between the two figures. If I skip down here to example 1, because we're not introducing any new concepts here, what I have is a situation that I've got those sides are congruent, those sides are as well, and I know that BD is exactly the same for both. It's the same segment. So now I can prove that those two triangles are going to be congruent based upon side, side, side congruence. I look at the information that I'm given in the drawing, and then I have to decide which of my postulates or theorems will help me then prove that the triangles are indeed congruent. Well, here's another situation. There's a lot of information in this problem, so I really need to break things down. One of the key elements is that I'm doing my drawing and I recognize that with my drawing, and it's shown here on this map, I'm working with right triangles. Now what I have to do, if I want to know that the two triangles are going to be congruent, I have to know, are my hypotenuse congruent, and do I have a leg congruent as well? Well, in this case, what I know is that when I draw this, I'm by definition making M the midpoint. And if M is the midpoint of LP, then I know the two sides are going to have the same length. The midpoint cuts it in half. Just so happens that these then are the hypotenuse. So I've got hypotenuses that are equal. I know that by two right triangles. And now I also know that these legs are equal, so that by using hypotenuse leg, I know that those two triangles are equal. And if I was given some information on the drawing, potentially that information or that information, I could find the total distance and even how far if I was to go directly across the river. So what I have to do, again, is break my drawing down to the pieces that I understand and then figure out what to apply to it. Here's an interesting situation because we're told that we've got some angles here that are going to be equal. I've got angles that are equal. And I also am going to show, let me erase that I know angle 1 equals angle 2, angle 3 equals angle 4, and I'm trying to prove BCE, that one, is going to be equal to DCE. So I'm starting with that example. Well, what do I know? First of all, I know that we've got sides, angle side, if I can show that CB equals CD. Because I know, since these angles are equal, that those two are going to be equal. And so what I'm looking to do is say side, angle, side. The way I would do that is begin breaking the problem down. And again, this is more about how to approach the problem, because what I ultimately need to do is prove those two are going to be equal in order to apply side, angle, side. So take a look at this example, read through the proof, and see then how we've applied what we know about all of these triangles and all of this information in order to show side, angle, side. When I have a drawing like this one, in examples 2 and 3, I have to break things down to see what I'm working with. Well, in this case, the ones I just drew, I've got two right triangles. I know that I've got a leg which is equal to each other, but I also know that since these two sides are equal, those two sides have to be equal. Therefore, I know that that triangle is going to be similar to that triangle because of hypotenuse leg. Again, what I have to do is I have to look at the figure that I'm being given and break it down in a way that allows me to decide which of the theorems or postulates can apply. So this is the last lesson in chapter 4. And again, it's going to be a culmination of how to evaluate and use side, 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 angle, side, hypotenuse leg, angle, side, angle, and angle, angle, side. So I've got those 5 tools to work with to either help me prove that two triangles are actually going to be congruent, or I can be told that they're congruent, and then I can find the corresponding sides in order to solve for maybe the length of a side or the measurement of an angle. If you remember back to the beginning of chapter 4, you remember that we talked about different types of triangles and being able to categorize them or classify them by either their sides or their angles. What we're going to be doing here in lesson 4.7 is looking specifically at isosceles triangles and equilateral triangles. If you recall, an isosceles triangle has two sides. They're going to be equal. We call those sides the legs. And the third side is we call the base. We have a specific term for the angles that are created between the leg and a base, and those are called base angles. If I know that I have an isosceles triangle because the sides are equal, I know that the base angles are going to be equal. And likewise, if I have a triangle where I have shown that the base angles are equal, then I know that I'm working with an isosceles triangle. So base angles of an isosceles triangle are going to be equal because we're working with two sides of a triangle that are equal as well. The way I can apply that is I know that in this drawing here, for example 1, that I'm working with an isosceles triangle. I'm told the two sides are the same length. So then by definition, I know angle F and angle E are going to have the same measurement. If I was given angle D, just one of them, I could figure out the other two because I know when I add up all three angles, they're going to equal 180 degrees. We'll take a look at how to do that in a bit. Here's a situation where I actually have a set of triangles, and I have to remember from the drawing that this is part of how I can evaluate the two smaller triangles. What I'm told with the bigger triangle, JKL, is that it is an isosceles triangle because I'm told that those two sides are the same. Well, when I draw a bisector from JM, now I know that those two sides are the same, this third side are the same. So now I've created two smaller triangles that, knowing using side, 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 I've taken my isosceles triangle, drawn a bisector, and created two equivalent smaller triangles. Again, what I've done is break down my drawing and evaluate it using side, side, side. When I'm looking at an equilateral triangle, by definition, because the equilateral triangle has all three of the sides equal measurements, the angles then are always going to be equal as well. So an equilateral triangle is always going to be equiangular. I also know that if I have an equilateral triangle, which is equiangular, if all three of the angles are the same measurement, and they have to add up to 180 degrees, I know that the measure of each angle of an equilateral triangle is going to be 60 degrees, because 3 times 60 is 180 degrees. So I can kind of keep that in the back of my mind. If I have an equilateral triangle, I know any of the three angles within that triangle will be 60 degrees, and they're all going to be the same. Similarly here, I know that from this drawing in example 2, since all three of the angles have the same measurement, it's equiangular. By definition, if a triangle is equiangular, it is also equilateral. Therefore, I know the other two sides here are going to be 5 because this side was shown to be 5 as well. Again, I just apply my theorems, either forwards or backwards in some ways, but it's the same type of concept going from angles to sides, sides to angles. I just have to remember what the relationships are. When I look at an example like this, what I'm going to have to do is evaluate what I know about my triangles. Well, the first thing I know is that this triangle is an equilateral triangle. I know that because all three of the angles are shown to be equal, there, there, and there. And since one side is going to be 4, I know by definition y is going to be equal to 4. So I get that just by evaluating the triangle itself. Now what I have to do is solve for x. The way I'm going to do that is by knowing that now this triangle has two angles that are equal. Well, to me, those look like base angles. And if base angles are equal, I know my triangle is going to be an isosceles triangle. And because of that, and because I know that this side was going to be 4, the equilateral triangle, I can set up my equation to say this side and that side are going to be equal. They're the sides of my isosceles triangle. And then I can solve for x as well. I break this down into two different triangles. I start with the equilateral triangle. I solve for y. then I see a second isosceles triangle, and then that's going to allow me to solve for x. Here's another example. I have an isosceles triangle here, and so I know some information based upon that. And then I have, this first one was an equilateral triangle, not an isosceles triangle, equilateral. The second one is an isosceles triangle. And then I also am given some information here that I have a right angle. So one of the things that I know is that because this first triangle is equilateral, I know x is going to equal 60 degrees. All three of the angles are going to be equal, and they're going to equal 60 degrees. Well, I know if x is 60 degrees, and this part of the angle here is 60 degrees, if the entire thing is 90 degrees, I know that side is going to be 30. So that's going to be 30, that's going to be 60. If that's 30, because here I'm looking at now an isosceles triangle, I know that side's going to be 30. So I'm able to solve y because 30 and 30 is 60. All three have to add up to 180. So now I know y equals 120 degrees. Again, what I do is I start by breaking my triangle down into things that I know. I recognize I'm working with an equilateral triangle, so I know what the angle measurements are for that. I see my right angle. I know that 60 from 90 leaves me 30. Now I'm working with this isosceles triangle, and I'm able to use my angle relationships and my side relationships to then solve for y. In lesson 4.8, we're going to be looking at a slightly different set of concepts. We've been working with triangles and triangle congruence, isosceles, and equilateral triangles. And now what we're going to be looking at is what is called congruence transformations. And basically a transformation is taking an object and moving it, basically an exact replica of that object, to a different location. So there are three ways that something can be translated, or three ways that it can be transformed. The first is the reflection. It's kind of like looking in the mirror. I've basically taken this image and I've rotated, if you will, about this line, this axis. So it's now flipped from the top to the bottom. The second is a rotation. So it's as if I have this on a stick and I just move the stick this way, and then every piece moves along with it. And the last is a translation, and a translation says I move along at a straight line. So here again I have different transformations, either reflection, rotation, or translation. In this picture, what I have is a number of zebras drinking in the water, and I've got a reflection of them in the water. I could draw a line, and that's the axis that the reflection has rotated on, if you will, or moved about. So then in this case, what I have is a reflection. It's pretty easy to understand because I think of images being reflected off the water anyway. So now, when I translate a figure, the way I can describe that on a coordinate plane is by how far each vertex moves. So each point is going to move over A up B. This one is going to be over A up B. This one's going to be over A up B, because I've taken and moved or translated that image from one place to another in a consistent way, which is why I start with my original XY coordinate for each vertex of this figure, and then I'm adding my A and my B to come up with the 3 new coordinate points for the red figure. So I'm taking the light blue figure there, maybe it's green, kind of looks light blue, and I'm moving it to become the red figure by moving it over A, up B. When I'm given 2 figures that are drawn on a coordinate plane, I can figure out what my translation is by looking at the difference from one drawing to the next. So in this case, I take this point and I look there, that point to there, and I can see I've gone from -4, 3 to 1, 1. So from -4 to 1, I've moved 5, that's positive 5. From 3 to 1, I've moved -2. And I can test that for every single case. I can see, does this work for every vertex? Well, when I add 5 to -1, I get 4. When I subtract 2 from 1, I get -1. And so I can see that I have set up my translation coordinate information correctly. When I have a reflection, I'm basically figuring out, am I reflecting around the x-axis or the y-axis? If it's the x-axis, then my x values are going to all stay the same. I'm staying on this side of the x-axis. My y values simply become negative. Likewise, if my reflection is around the y-axis, my x values haven't changed. I'm above the x-axis in both cases. My y's haven't changed. My x's now become negative. So if this is 1, that's -1. If this is 5, that's -5. So my y value doesn't change, but my x value just becomes the negative. So depending on if I'm reflecting around the x or y axis, around x, y becomes negative from its original value. If it's around the y, x becomes negative from its original value. And so what I'm given here is an example of half of a drawing that I want to reflect around the x-axis. And I want it to be an exact replica. And so I can look to see, well, my first one is at -1, 2. So I see that point. Well, I still want it to be -1, but now I want it to be the opposite of 2, so it's going to be -2. So -1, 2 becomes -1, -2. And I do that for every single point. That point is 1, 1. I'm reflecting around the x-axis, so it's y that changes. And so, that's 1, 2. So here it's going to be 1, -2. I do that for every point, and now I have a reflection around the x-axis of my original drawing, and I do that by keeping my x values the same, but making it -y, because again, it's around the x-axis. In this case, I'm just showing an example of a rotation, and the amount that I rotate, I can measure in degrees. So what I have in this first drawing is I've taken, and basically it's like, again, it being on a stick and moving the stick over here, and I moved it 90 degrees. So ultimately that would be a right angle. Clockwise, the way the clock is moving. In this case, I've moved it 60 degrees counterclockwise, but it's the same kind of thing. I think of as if I have the drawing on a stick and I move that down and I moved it counterclockwise, 60 degrees. And so I'm going to move from here down to here. In order to solve example number 4, what I have to do is I have to plot all of my points, and then I have to take a look because I'm looking at AB as compared to CD, and I can see that I have rotated this 90 degrees around the y-axis. It's clockwise, so I'm going that way. So I've made the rotation and moved it over here. And in this case, I don't have a rotation because the direction of my figure has changed. This movement is different than that movement. And because of that, it's not a rotation. I've moved them different amounts. What we're going to do now is just going to have you go ahead and go into the exercises now. And I think that's going to help you then evaluate the drawings and determine what kind of a transformation that you're working with.